Good afternoon, everyone, and welcome to the latest edition of ODSC Lightning Interviews. Hope everyone is looking forward to what I'm sure is going to be a very well-deserved weekend break. And as always, if you've joined us before, we do want to make these sessions both interesting and interactive. So please do introduce yourself, share your story, tell us where you're from, and tell us about your interests. Now, before we get started with today's interview, a few quick points about upcoming events at ODSC and AI Plus. So as always, we do have a very active calendar. We have events, free webinars coming up on March 1st and March 10th. We also have live training starting on March 3rd. By the way, if you've got a QR code reader on your phone, you can scan that screen, and each of these QR codes will link directly to the events. In addition to that, you may know we're doing a deep learning bootcamp with the ever popular Dr. John Cron. I think that's on the third session at this point, the third course of that 6-course series, and you can get the first 2 on demand and then pick that right up. And then, of course, we do have ODSC East in Boston happening on April 19th to 21st. That is a hybrid event for us. It is both in person and virtual. So if you're in the New England, Boston area or feel like getting a flight, please join us. And in addition to that, I think we have another slide on it. We do have a free AI Expo Hall. So this year especially, we've got some of the top companies in the AI startup world participating. So very, very excited to have them join us at ODSC East, both in person and virtually. So register for free. You can see the link there in the QR code, or just go to odsc.com Boston and you will find out. And then in addition to that, do not forget about our AI Plus Careers website. That is actually a free community resource. We started during the pandemic. You can upload your resume. It uses machine learning to help match you with jobs with our community partners out there. So it's free to post a job on there. It's free to participate, and you'll get lots of recommendations on various jobs. So when you have a chance, please update your resume there. And in addition to that, I believe we are running a virtual career fair at ODSC East. So if you're in the job market, want to talk to some data scientists about various positions, check that out. And I think that's our last slide. We have, you're right. Okay, great. So I would like to bring today's guest to the front of the stage. And as a reminder, if you haven't used this platform before, whether you're joining us on Twitter or LinkedIn or YouTube, you can actually post questions. So in addition to introducing yourself, please post any questions you may have for myself or Carl at MLOps at Scale. So Carl, welcome to the show.
Hi, Seamus. Thank you for having me on the show.
So excellent. So Carl Osipov is he has worked in deep learning and machine learning at both Google and IBM, and currently is a senior director of ML and AI solutions at Cognizant. And Carl is also the author of a very recent book on MLOps at Scale, as you well know. And Carl, I think you have some good news for us about that book. You mentioned that you may be giving our audience a few copies, and I've read the book myself, and I can highly, highly recommend it. We'll get into the book in much more detail. So if you wanted to mention that at the start off, Carl.
Yes, I appreciate you mentioning that. So let's do the following. How about we give out free copies of the electronic version of the book, PDF, EPUB, and similar, to the first 10 people who will email me with that request. Let's say they'll put the MLOps engineering at scale in the title of the email and email me to my first name, last name @gmail.com. So Carl Osipov @gmail.com.
Excellent. And yeah, to our viewers and listeners, you'll actually see that message and that email below in the message box on your screen. So Carl, tell us a bit about yourself. Tell us about your journey to through software architecture to machine learning. Love to hear more about that.
Sure. So I guess the audience here is interested in the deep learning dimension. So let me start with that. I've been fortunate to do undergraduate research with one of the founding members in the Carnegie Mellon Connectionist School. So the same school that included well-known individuals like Jeff Hinton, Jan LeCun, Michael Jordan, and others. So by the virtue of that fact, I actually implemented my first neural network back in 2000. So back then it was just 2 hidden layers, and we used to think that was enough.
Yeah, that's right.
The network was written in C, so just backpropagation, hard-coded, with sigmoid activation derived by hand from calculus. So definitely not something I would recommend today. But I think that exercise in applications of that neural net implementation told me that we just didn't have enough compute back then. And that really impacted the continuation of my career in the industry. So after the research, I went to IBM. I focused there on software engineering, and also software engineering in a particular niche. So software engineering of distributed systems, think high performance compute, distributed systems for big data analytics, for machine learning eventually, and essentially just helping IBM build out these systems for various customers, large banks, insurance companies. So specifically, I was building out Hadoop and then later Spark-based systems. And I think that is what follow role at Google. So at Google, I've been fortunate to manage Advanced Solutions Lab Fellow, one of the top folks in machine learning at Google. That was very exciting. Worked with over 2,000 customers and partners of Google Cloud, and learned quite a bit about what it takes to put a machine learning system into production. So there, I think the theme of the effort at Google was to help democratize machine learning and AI. So hopefully that's enough of a background.
That's an excellent background. And as you mentioned, Carl, you were first a software architect, and then you became an expert in machine learning and deep learning. And that definitely comes through in the book, because I do notice that machine learning, data science first engineers, they sometimes struggle with software architecture. And I do see that you captured that extremely well in your book. And that's a good blend of software architecture and bringing those practices to machine learning, which we'll get into a little more. But, just leading in off that. So, so you talked a little bit about your experience, but what was the inspiration of writing this excellent book, MLOps at Scale?
Right. So I mentioned that at Google, my focus has been on this theme of democratizing AI. And I think the book is partially motivated by my frustration with how the industry went about it. So after I left Google, I actually co-founded my own consultancy, and I work with many customers. So I work with primarily Fortune 500 companies while at Google Cloud. At my own company, I worked primarily with, let's say, a regional food delivery company in Southeast. And I think what came across in my experience is that while the industry really focused on the enabling technology, so when I say enabling technology, I'm talking about frameworks like TensorFlow, Keras, right, scikit-learn, and more. That's not really the area where data scientists and machine learning engineers have had difficulties. So I think these are, folks who go into machine learning are brilliant minds. They are able to pick up these frameworks quickly, and they're able to use these frameworks to create experimental machine learning code. The challenge really comes in later. So I mentioned, my own consultancy there. When working with customers, right, I found that companies really struggled with taking those experimental ideas implemented using machine learning frameworks and putting them into production. So this means how do you ensure rapid experimentation? How do you try different ideas and then put those ideas into production? How do you think about the life cycle of the solution, right? So not just the ideation of the solution, not just some of these early experiments, but how do you think about the system running in production and operations, right? MLOps aspect. Right. And how do you have the right machine learning platform to help you do that? So really that's what prompted me to write the book.
No, it's impressive because ODSC was just starting to look at machine learning workflows and MLOps, and back then we were calling it, an extension of DevOps, which it still is, and data ops and AI ops. And I know it takes a lot of effort and a long time to write a book. So the book itself, I feel, is very, very timely. And because, when you look at the most popular algorithms and models used in a lot of companies, when you look at the results from surveys from various people who run these surveys, you'll see like the top algorithms are still logistic regression, random forest, and these models tend to work very, very well in small to medium-sized data sets. So a key question here is like, why does scaling, like the title of your book is MLOps at Scale, as opposed to just MLOps. So why does scaling matter so much in your opinion?
Yeah, right. So you mentioned earlier my background in software engineering and software architecture, and I think that really influenced the scale dimension in the book. So scalability, it's such a multifaceted topic, and when I think about it, there are different subtopics that I can cover, but we only have limited amount of time, so let me focus on just a few. So I'm going to cover 4 angles. I'll talk about scalability from the standpoint of data, model parameters, compute, and then I'll also talk about scalability from the standpoint of networking bandwidth. So that might seem a little bit surprising, but I'll tie that back into the discussion of training these large-scale deep learning models. So let's start with data, because I think that's the one that's most obvious. Clearly, there's a lot of knowledge in the industry around big data. And then if you take machine learning in particular, there's the classic research paper from Peter Norvig and others about the unreasonable effectiveness of data. And in a nutshell, the paper is all about the observation that Google researchers had that more data in simpler models are better than more elaborate models and less data. So here, when we're talking about data, I'm talking about data that is at the scale used by Google search engine. So think about trillions of words. And the idea of the paper is that if you want to build effective machine learning models, it's very worthwhile to invest in acquiring more data, right? So that's one dimension of scalability. How can you, as a practitioner, ensure that you can scale to large data sets? Now, another angle of scalability is all about model parameters. And I wish I had the time to put more about this in the book. Actually, I don't get into this topic in the book all that much. But there's a fascinating research paper that came out recently about the law of robustness. So if you haven't seen this paper, I really recommend it. So it's by Bubeck and others. And the paper makes a very solid mathematical argument that today's deep learning models are under-parameterized. So even if you take classical image data sets like ImageNet, so the paper actually makes an argument that right now the number of model parameters that we're using to build models for ImageNet is somewhere 10 to 100 times fewer than what we really need. And as a consequence of fewer model parameters that there should be, we're seeing the kind of behaviors that we're right now describing as lack of robustness to adversarial examples, right? So a classical example is when you take a picture of a cat, tweak a few pixels, and then suddenly it gets recognized as a dog, right? So I'm still working on understanding that paper. As I mentioned, it came out late. I book writing process, but I think that's an important dimension of scalability. And if you're interested in this issue of scalability to more model parameters, definitely I recommend checking out that paper. And then I also mentioned that in addition to data and in addition to the scalability relative to model parameters, it's important to think about compute. So in the book, I make a reference to another, this is really an article from Rich Sutton of the reinforcement learning fame. So Rich Sutton actually wrote a nice article, a blog post called The Bitter Lesson. And it reviews the past 70 years of AI and talks about the fact, or the observation really, that the methods that have been relying on using more compute capability have generally been more effective than the methods that rely on handcrafting models. Right. So this echoes back to the question about scalability to large data sets, but this focuses more on compute, right? So this is really about scalability in terms of data, in terms of memory, in terms of compute. And I'll mention briefly this last one because it's important to the approach taken in the book itself. So in the book, I make the argument that if you do need this kind of scalability, the kind of scalability that you just described, the way to go is to build your machine learning system in a cloud computing environment. So for some people, this might be obvious. For others who might be using GPUs in a high-powered server, maybe not so obvious. But the point is that with cloud computing environment, you have the flexibility of scaling and scaling in a cost-efficient manner. And one of the dimensions in this distributed cloud computing environment, you're using things like network bandwidth effectively. So this might be a little bit surprising, but in the book, I get into the relationship between distributed training for deep learning and how that translates into usage of bandwidth as well.
Yeah, there's a great chapter about distributed training in the book, and I would like to get to that a little bit later. And yeah, that was a very insightful summary of those various points, Carl. Thank you for that. And when you were writing this book, who was the audience that you had in mind primarily for this ML ops at scale?
Yes, thank you for asking that, because I just realized that in my answer to your last question, I probably made the answer sound too theoretical. I cited a few research papers. So if you are interested in the book, don't expect this book to make you a world-renowned researcher. And even if that book helps you in your PhD or in writing your next research publication, please let me know. But that's not really the target audience for the book. I would say the book is very much written from the applied point of view. And it's really targeted at software engineers, clearly someone who had more of my background, but generally also to industry technology professionals, data scientists, data analysts, and others who may have experimented with machine learning. Maybe they took a few online courses, tried out a few things, but now are interested in taking the next step. So by that, I mean, after experimenting with machine learning, okay, how do you make this valuable? How do you take these ideas and put them into production? So ultimately, I think the book is targeted at those who want to become more valuable contributors, have more positive impact on their project, their team, their organization.
No, that's a great summary. Yeah, and I would second that as well from my reading of the book. I was a software engineer first and moved on to the machine learning and data science. And I definitely saw the advantage of that. And I would say for those of you who are machine learning, data science first, I would say, you already feel like you have a lot to cover in your career when you're learning. But this is an excellent book to get a good idea of the software architecture that's involved in machine learning workflows, which is very important these days. Now, want to switch topics a little bit. Earlier in your book, chapter 1, I think it was, you mentioned yak shaving. So tell us a bit more about that. And don't worry, viewers, we're not digressing too much.
So frankly, I'm surprised that this phrase is not better known. So when I started interacting with more of data science people, machine learning people, I brought up this phrase and I got a lot of blank stares. But the phrase actually originated from the MIT AI lab back in 1990s. And I found it's fairly well known, at least it used to be well known among IBM software engineers. So what is yak shaving? So in a nutshell, yak shaving refers to the situation that I'm sure most of you found yourself in. And it's that situation where you're trying to solve some important task, but then you find yourself digressing into something seemingly unrelated, but necessary to solve the problem for some weird causal chain. So in the book, I give an example where you are trying to improve the performance of your cross entropy measure while working on the classifier. And then you find yourself reinstalling the Linux distribution because you need to be up to date with the latest drivers for a GPU that you're trying to use to improve the experimentation agility as you're rebuilding your model. So that would be one example.
Excellent. Yeah, and if everyone's ever seen a picture of a yak, very long haired, so imagine trying to tackle a yak with a razor blade or something like that. So that'll give you a good analogy of what you're involved here. So yes, and also in the tangential related to that, you did mention earlier on in your book on the subject of hidden technical depth in machine learning systems. And there's also been some quite good research papers about that. So can you talk a little bit about that as well?
Sure. It sounds like you're mentioning topics from the first chapter of the book.
Yes. I didn't read more than the first chapter, by the way, but I thought it was an excellent introduction to the whole topic.
Right. Yeah. So hidden technical debt in machine learning systems. So this is a paper from Scully and others from Google Research. And I think for the MLOps, this is very much a foundational paper. And there's a famous diagram in that paper, which is reproduced in the first chapter of my book. So what folks from Google found in their experience in deploying machine learning systems is that these systems, once they get to operations, they end up being only about approximately 5% machine learning code, with the remaining parts of the system effectively acting as supporting infrastructure. So here, let me mention some terminology that I use in the book, where I draw the distinction between the machine learning code, ML code, and the ML platform. So ML code is that 5% that I just mentioned. And the ML platform is the remaining 95%, which is necessary in order to deliver a system into production. So this can include everything from data ingestion to reporting to some systems that have to do with data storage and analytics of column structured data. So think about everything that goes into making a working, productive, real world machine learning system. And in the book, I describe essentially the ML platform and talk about what it takes to create this kind of a platform. So I talk about the buy versus build decisions for the platform. So do you actually want to create your own version of something that is Tesla trying to do with their Dojo? So if there's the funding for that, that's awesome. But for the rest of us, I think there's some requirements that lead to machine learning practitioners essentially choosing to buy the ML platform for the most part. So what are the kind of criteria that you need to consider when purchasing an ML platform or the foundation for the ML platform? And generally, you have to realize that that platform needs to be reusable, right? So because otherwise, if you're not purchasing a reusable ML platform, every time you need to redo your machine learning code, you have to redo the 95% of the system. Then you also get into the other qualities, like obviously, if it's reusable, it needs to support multiple projects at the same time, potentially multiple organizational units in your company, maybe multiple machine learning engineers working in parallel, which in turn brings you to the question of multi-tenancy. So how do you securely isolate these users of the platform from each other? How do you set up administrative controls to manage it? And effectively, I make a connection from these requirements to the idea of a cloud computing environment. So in the book, I base all the examples of the project around AWS, Amazon Web Services, but the same ideas apply to other platforms as well, such as Google Cloud or Azure and similar.
Excellent. And that reminded me, you've already touched upon this, but training is obviously a major part of machine learning workflows, right? And you mentioned in distributed training, so all of our audience is pretty familiar with standard training of machine learning models and data science models. But tell us a bit more about the unique challenges of distributed training, the need for it, and some of the challenges involved in distributed training.
Right. So the topics or the chapters that have to do with distributed training are, I think, are the deepest in the book, and they're surprisingly subtle. I say it's surprisingly subtle for the following reason. So if you're a machine learning practitioner and if you pick out a framework like PyTorch and try to set it up for distributed training, On a surface, there's not much to do. So there are a few parameters that you have to configure, like the world size, the number of nodes that you have doing the training. You have to set up ranks for individual compute nodes within that world size, as PyTorch calls it. You have to call a few APIs. So it seems like it's easy. But once you go into production, you'll find out that this can break very, very quickly. And unless you understand what's going on behind the scenes, it's difficult to resolve those issues on your own, especially if you're more of ML engineer, more of ML ops practitioner. So I mentioned that in the book, there's some subtleties related to distributed training. And one subtlety is the relationship between automatic differentiation and distributed training. So what is that about? In the book, I get pretty deep into what it means to do automatic differentiation. So in the book, I use the concept of a very simple machine learning model to illustrate automatic differentiation in PyTorch. And then in the chapter that has to do with distributed training, I build on that and describe the how the gradients that are computed during training of a deep learning model, how do those gradients need to be communicated across compute nodes in a cloud computing environment like AWS? Right. So here, one of the things that a practitioner needs to understand are the networking bandwidth implications and also reliability of implications of distributed training. Even today, a lot of these distributed training approaches, or at least the ones that are commonly used in cloud environments, rely on what's known as a parameter server-based approach. So what does this mean? In practice, this means that the gradients that are computed during training of a deep learning model, they are sort of broadcast over the network. And in the book, I explain why broadcasting is really the worst case scenario for traditional computer networks. But everybody here probably has some intuition that broadcasting of things like video is very cumbersome for modern internet. So even though it works, companies like Netflix had to build out a lot of infrastructure in the modern web in order to support broadcasting of their video content to end users. So to that point, in the book, I describe the difficulties that exist in parameter server-based training approach and contrast them to ring-based server approaches.
Oh, yeah.
So the famous example is from Uber, for instance, a company that does the ride sharing. And Uber released an interesting algorithm called Horovod that describes training of deep learning models using this using this ring-based distributed training. So in the book, I explain why these ring-based approaches are efficient and in some cases optimal from the bandwidth utilization point of view. I get into the details of how they work and generally give some guidance to the practitioners when to pick which approach, right? When do you go with parameter server-based approach versus the ring-based approach? So ultimately, I think understanding these topics will make you a more effective practitioner, because once you hit problems such as in bandwidth utilization or with stability of your machine learning platform, you will have enough of the conceptual background to resolve.
No, excellent, Carl. And I would encourage our viewers to get your hands on that book, take a look at it. It's one of the best descriptions of distributed machine learning training I've seen in a long time. So that was very well done. Now, we've touched upon quite a few topics on machine learning workflow, but what are some of the other major challenges you see when designing a machine learning platform, especially one, again, that needs to scale, that we haven't touched on yet?
So I have an answer about a major challenge, and I think given the timing when we're doing this interview, it's top of the mind for many technology and business leaders in the ML and AI field, and that's expertise. So I would say, no doubt right now, finding the right expertise is the challenge, and it's very hard to find machine learning engineers, especially the ones with the right mix of expertise in machine learning and in distributed systems, specifically cloud computing. So I gave an example of a company like Tesla, which is well capitalized and can effectively afford to, I would put it as, corner the market on the expertise, build a moat around their business that way. But for many companies out there that need machine learning engineers, the solution is to make sure that their own talent, right, the employees of these companies, have the opportunity to grow their careers, right? If they're employees who take their careers seriously, they want to grow in their roles, have the necessary time, resources to study, have that grit to climb the learning curve. I think ultimately, once they climb that learning curve, that will help them climb the career ladder as well. So I think my book is very much written for this audience, for the folks who want to study, own the help of their companies that they work for, with the help of their teams, and ultimately make themselves more effective machine learning engineers.
No, that's great. And speaking of careers as well, like MLOps, again, the term's been around for 2 or 3 years now, and it's very, very well used, if not overused, in kind of a big tent, big umbrella kind of expression. But it was derived originally from DevOps. So can you talk a little bit about, the intersect of DevOps and MLOps, if you can expand on that topic a little bit, Carl?
Sure. So I think it came across in our conversation that I am biased by my software engineering background, but I think it's not controversial at all to say that machine learning systems are software systems, software-intensive systems. So from that standpoint, much of what we know about DevOps applies to machine learning. And of course, from the DevOps standpoint, automation is one of those critical intersection points. So when I say automation, I'm talking about things like continuous integration, continuous delivery pipeline. So in fact, in one of the recent projects that I worked on with a major online matchmaking website, one of the key challenges has been taking the experience that the software engineers have had in building out CI/CD pipelines and bringing that into the world of machine learning. But I think automation doesn't end there. It also covers things like test automation. So in other words, how do you make sure that as the engineers, as the machine learning practitioners are putting some tests around the functionality of the system, the performance of the system, that there's a way to automate checks of those systems against the tests. And also it covers things like infrastructure as code. So infrastructure as code is a major part of my book. So I talk about the fact that it's important to be able to provision the infrastructure in a cloud-based environment rapidly, and then just as rapidly, one needs to be able to tear it down. And that's what provides practitioners with cost efficiency in the cloud. So I talk about the use of infrastructure as code, and ultimately, I think these dimensions from DevOps, CI/CD, testing, infrastructure as code, these are probably top 3 that come to mind when I think about the intersection between the two. But ultimately, what I want to say about this relationship between the DevOps and ML, ultimately, I think it comes down to this idea of agility, right? So agile software engineering is a big part of modern DevOps. And I think what machine learning practitioners need to study in more detail, or need to pick up from the DevOps practice, is this idea of accelerating the life cycle of a system. So that basically means getting into the kind of patterns that software engineering practitioners have, where new features, new capabilities are introduced into an ML system daily, and then the velocity of releases, the velocity of deployments goes from once a quarter to something that can support multiple deployments of new features, new capabilities per day. So I think we're still missing that, the intersection between MLOps and DevOps.
Yeah, I can definitely agree on that, Carl. So again, I'll just remind our viewers, you can pose your questions for Carl, and we do have a couple. One from Hermat Kumar, and he wanted to know if you can differentiate your books and how much is involved in hands-on practice, or is it more theory?
Yeah. Good question. So we've been talking about MLOps at fairly high level. So the entire book is actually structured around a project. So I mentioned that at my own consultancy, I worked on this food delivery application. So some of my learnings there went into the book. And the book is structured around this specific use case in delivery and logistics, which is the ETA problem, or estimated time of arrival. And in the book, I basically take a data set and use that data set, single data set, throughout the entire book. So I start with the data set of these car rides in Washington, D.C. I go through the process of preparing that data set, show how to clean it up, show how to build a PyTorch-based deep learning model around it, how to implement that model, scale it, eliminate boilerplate in that model, and ultimately prepare it to go into production.
Great. And touching upon that a little bit, you cover serverless machine learning in your book quite a bit, and serverless machine learning in software engineering as a concept has been around quite a while, and now it's definitely creeped into the machine learning workflow lexicon, definitely with as an ML topic. And I'm sure many of us on this call are familiar what serverless compute is. But if you can just give us a brief overview of that, Carl, and then how it relates to its importance within machine learning workflow. Love to hear that.
Right. So serverless is definitely this topic that came about from more of DevOps, more of software engineering side of things. And as I mentioned, there's quite a bit of overlap between that and modern ML ops practices. So for those who are not familiar, serverless is this concept of executing code, usually in a cloud-based environment. And serverless is one of those terms that seems nonsensical at a glance, because how do you run your code without servers? But in a nutshell, serverless is not about the fact that your code runs without servers. The servers are still there to run your code. It's more about the experience of writing code in a way that helps the practitioner, helps the developer forget about the fact that that code can be put somewhere in a cloud where it actually runs on the physical servers. So in practice, this means that the developer can focus on writing, let's say, their deep learning model and not have to worry about what kind of operating system that they're running, not have to worry about patching and updating that operating system against the latest security advisories, maybe managing middleware and more. So ultimately, the way that I look at serverless for machine learning is about making the practitioner more productive. So this means that as a practitioner, you can build your code that might be preparing data or cleaning up data. You can prepare code that helps you do analysis on that data, or even maybe just train your ML model. And then you pass that code over to your cloud provider and let the cloud provider handle these kind of operational details. So this is what makes the practitioner more productive. And in the book, I take a very broad view of serverless machine learning. So I mentioned that this is not just about deploying into something like Lambda or Google Cloud Functions-based environment. This is really about using all these features of cloud providers that manage the underlying infrastructure. So for instance, in the book, I show how to write your scalable data preparation code, everything from data ingestion to data cleanup to data analysis using AWS Glue specifically, which is Apache Spark-based environment, serverless Apache Spark-based environments, and then continuing from there, essentially using serverless tools to help you train your model and more.
Excellent. Now, you mentioned earlier in the interview about PyTorch, and you have devoted a few chapters in your book to PyTorch. And I believe in your past roles, you were an expert in TensorFlow. So I think you'd be a good person to answer this question. And that seems to us that PyTorch definitely seems to be gaining traction on TensorFlow. Why is that?
So at Google Cloud, 100% of my time was spent on helping customers build out TensorFlow-based systems. And then after I left Google, I switched to PyTorch, and I haven't looked back. So if you're asking why, I think the short answer is that PyTorch provides or offers a better development experience to practitioners. And there are many underlying reasons for that. One, I think, is timing. I think PyTorch matured just at the right time when TensorFlow 1.x started seeming outdated to practitioners, and Keras and TensorFlow 2.x hasn't caught on yet. So I think PyTorch was the right solution at the right time. But personally, I like PyTorch for other reasons. So I like PyTorch because of the strong documentation, strong, well-designed, consistent documentation. I like PyTorch because it gives me access to the underlying automatic differentiation and gives me quite a bit of control over that. So I think that's important once you start getting into distributed training and these other topics. And ultimately, I think PyTorch is just more fun to write PyTorch code.
Excellent. Yes. So we covered a lot in MLOps, but what do you think is next for MLOps? Like, what are either some of the unsolved problems, or what do you think? Because there's a lot of startups building out MLOps platforms. There's a lot going on in that space. One would think with all the activity we've solved all these MLOps problems. And we've talked about a few challenges already that haven't been solved. But what do you think are we going to be seeing in the next coming months and years around the MLOps space?
Okay, so I'm going to hedge a little bit because we're talking about the future and what are we going to see there. So I'll make a little bit of a safe bet. And I would say that MLOps is going to start to look more like DevOps. So that shouldn't come as a surprise to anybody, but there's a specific area of DevOps that I think is still diffusing its way through MLOps. And that is everything having to do with culture. So mature DevOps organizations are quite good at creating a team-based culture, which is built around things like transparency, collaboration, communication, and I think MLOps still has quite a way to go there. And I think one of the problems is, let's say, academic training, which is very strong for many people who go into machine learning engineering and end up in MLOps. So I find that academia fosters this approach of taking a problem, going out on your own, solving it, and then returning back with a solution. And this is very much against core principles of culture in DevOps. So to give you an example, actually, I'll continue with that example of working with an online matchmaking company. So I'm sure all of you can think of some of the brands that are out there that help people date each other. But specifically within that company, I worked with a very strong machine learning engineer. And we tried to create this agile culture, institute DevOps practices. And for the ML engineer, the task was, apparently obvious, right? Pick up the data set, go build a model, and then come back with a solution. And the challenge with that approach is that in a DevOps practice, the responsibility for the solution is shared across the entire team. So it's important not just to be able to come back with the best solution. It's important to come back with a solution that can be supported by the entire team, and the entire team can hold the responsibility and be successful supporting that solution. And in some cases, this means maybe finding a solution that's not just best for the data set and for the model, but finding the solution that works well for the kind of infrastructure that the team can support, works well for the kind of CI/CD pipeline that the business objectives are driving, right, in terms of the number of deployments that one wants to accomplish per day, or the kind of automation and test automation that the organization wants to set up. So I think more transparency, better collaboration. I hope these kinds of cultural values will be more prevalent in MLOps as this field matures.
Excellent, nice insights, Carl. So we're coming up to the top of 45 minutes, which is usually our max time, but we will take one more question from our audience. Now, Elon Moyala has a very good question, and that is, how can I leverage MLOps to create systems that are not heavily reliant on the internet? Let's say for creating projects that impact places with low internet connectivity. And we've gotten this question quite a few over the years. And I think a very interesting one, we're talking about MLOps at scale. So places with low internet connectivity. And I think you've already kind of answered some of those questions because it is serverless, it is somebody else's cloud. But go ahead, Carl.
So I would say the approach taken in my book is not mutually exclusive with your use case. And here's why. So the places with low internet connection ultimately are the places with the effectively low bandwidth, right? That's what you're describing. Low bandwidth, high latency. And I challenge you to think about cloud computing environments as virtual test beds for what you're describing. Because in modern cloud computing environments, you can easily simulate the environment with low bandwidth, high latency. It's basically something that you can do as part of the configuration of your environment. You have control over that. So think about using cloud as a way to develop the solution with your target, geography or target target quality of service requirements in place. And then actually, once you develop that solution, take the next step and push out that solution to the edge, right, to the edge of the internet. So whether it's cell phones or, I don't know, low energy devices, Raspberry Pis, and so on. So simulate them in the cloud, make sure you can get things done in that familiar environment first, and then move on to the next phase where you actually go into production in your specific region, your specific environment.
Great advice, Carl. Thank you so much. And last but not least, people want to follow you, get in touch with you. I know we've shared your email to get those copies, those 10 free books, but are you blogging? Are you on LinkedIn?
I'm not blogging as much as I should, but feel free to reach out to me on LinkedIn. It's just Carl Osipov. I think hopefully I'm still the only one there under that name. Yeah, if you want to reach out, feel free to email me.
Yeah, and Carl, it's a pleasure having you on the show. You did speak at one of our ODSC conferences a number of years ago. You know, when your busy schedule permits, we'd love to have you back to speak on this and other topics. So thank you once again for taking the time out of your busy schedule, and we will chat again.
Thank you for the invitation, and thank you for having me.
Excellent. And to tune in a couple more weeks. We'll be having follow-up sessions. So thank you, everyone, for listening in, and we shall meet again. Thank you.